This meeting is being recorded.
In this video, I'll cover the second part of problem 3 from chapter 11. In a different video, we looked at the solutions for parts A through D. So in this video, we will solve parts E through H. So similarly to that video, we are asked to propose an efficient synthesis for each of these transformations shown below. And in our first reaction here, as always, we're going to look at our functional groups in both the product and our starting material and see if the identity has been changed or the location. So the functional group has remained the same. We have a hydroxyl, so alcohol, functional group on both the starting material and the product, but the location has changed. So how can we accomplish this? So first we can perform an elimination to generate this intermediate product here. And that can be done in a two-step process. First, we would convert that alcohol to a better leaving group. So we could use tausyl chloride, right, and pyridine. And then in a second step here, we could then use sodium ethoxide to give us our Zaitsev product here with this elimination. And that gives us that intermediate, but we still need to convert this to an alcohol. So we could use acid catalyzed hydration and add HOOH, right? We can add H2O to our double bond using this reagent here. So just H3O, hydronium, for that acid catalyzed hydration. So that is E. Let's take a look at what we see in F here. So again, we'll begin by analyzing the identity and location of functional groups in both starting material and product. So we have this halogen, then we have an alcohol. So this has changed not only position, the functional group, but the functional group itself has changed. So with this type of transformation, we could accomplish this using, again, a two-step process. We could do elimination of HBr, right? So we'll do an elimination, and then followed by an addition. So then we'll add H2O in the second step. So we can to generate our Zaitsev product that's shown as our intermediate here, we could use something like sodium methoxide to generate that more highly substituted intermediate. And then to add H2O in a Markovnikov fashion, we could again use acid catalyzed hydration. So we wouldn't need this if we broke them down. We wouldn't need that number 1. But if we, sometimes you'll see steps written one after the other. So then we would need to indicate here that they're two distinct steps if we were to combine them. So let's take a look at G. So again, we analyze, this time we go from OH, so an alcohol, to our halide over here. So we've seen this type of transformation accomplished with elimination followed by addition. Instead, let's see here. So we can remove that alcohol group, but first we need to convert it to a better leaving group. So we can again use that tausyl chloride in pyridine. And then we want to generate the Hoffman elimination product here. So we would have to use a sterically hindered base such as tert butoxide potassium. So then we end up with this intermediate here. To go from that alkene to this alkyl halide, we could use an anti-Markovnikov addition. So we would add HBr and use an organic peroxide as well. In our last reaction here, Let's do our quick analysis. We have alcohol, we end with alcohol. So functional group remained the same, only the location changed. So let's go from this alcohol to this alkene, just like we did in the last reaction. We would use tosyl chloride and pyridine, and then followed by our elimination using tert butoxide, the more sterically hindered base. Once we reach that point, there are actually two different mechanisms that would generate this product. So we could do, in this two-step addition, we could add in an anti-Markovnikov fashion, and then we can do a SN2 substitution using a base, sodium hydroxide. So again, this would be an SN2 mechanism. Or we can also generate this alcohol through hydroboration oxidation. So we could use BH3 and THF in step 1, and then we have our peroxide in basic conditions.